everybody. Hope you had a great weekend. We've been talking so far about how to find various derivatives. So far we know how to find derivatives of polynomials, e to the power of x, and products and quotients with those things, polynomials and e to the x. We also now know how to take trigonometric derivatives. This lesson 3.6 is about some applications of derivatives, specifically speed, velocity and acceleration, growth rate, and marginal and average cost. We're not done learning how to take derivatives. This is just a pause to briefly explore some applications of derivatives. Our mathematician of the day today is Alan Turing, who was a 20th century mathematician who broke many encrypted German codes during World War II. But his brilliant career was cut short when it came out that he was not heterosexual. If you've ever seen the movie The Imitation Game, it is all about Alan Turing and what he did during World War II. It's a fantastic movie that I highly recommend. And did you know that the symbol pi was not used in written mathematics until 1706? Until then, they just wrote out like 3.14159. So pi is a lot easier to write out. So I'm glad that they adopted that in 1706. All right, so today we will be discussing derivatives in terms of rates of change. So far we've been discussing derivatives as slopes in terms of a specific equation or graph, and a slope is a rate of change in a graph, but today we'll be talking more about applications. So first we are going to define speed, velocity, and acceleration in terms of derivatives. So suppose an object moves along a line with position s is equal to f of t. Then the velocity, velocity at time t is given by v equals the derivative of s, which is our position, or f prime of t, since we have s equals f of t. So if I'm given a position function, the velocity is simply the derivative of that position function. The speed at time t is given by the absolute value of v. So speed is just how fast the object is moving, but it doesn't matter if it's going forwards or backwards. So this is the same thing as the absolute value of f prime of t. And the acceleration of the object at time t is the derivative of the velocity. So this is the same thing as f double prime of t. So if I have a position function and I take the first derivative, that is the velocity. And then if I take the second derivative, that is acceleration. So we have an example here to show us how this works. Suppose the position in feet of a dog is given by s of t equals t cubed minus 4t for t between 0 and 5. We want to graph the velocity function and determine when the dog is stationary, moving to the left, and moving to the right. So I first need to determine what my velocity function is. So I know that the velocity is the derivative of the position. So I need to take the derivative of t cubed minus 4t. And if I take this derivative, I bring that 3 down and lower the power by 1. So I have 3t squared minus 4. This is my velocity function. And if I were to graph this, I don't expect you to know how to do this, but if you were to graph it, it would look something like this. However, we are only, our t is only valid for 0 to 5, so all we really care about is here on over. Alright, and now I want to determine when the dog is stationary, moving to the left and moving to the right. So if you think about the position of anything, it's stationary when the velocity is equal to 0. That's what it means to be stationary, it's not moving. So I am stationary when the velocity equals 0. So I'm going to take this function right here, and I'm going to set it equal to 0. So 3t squared minus 4 equals 0. If I add 4 to both sides, I get 3t squared equals 4, or t squared equals 4/3. I only care about the positive answer here, so I get t is equal to the square root of 4/3. In terms of our graph of the velocity, that is this point right here. So I can see that at this point right here, this is the point square root of 4/3 comma 0. That is when our velocity is equal to 0. Sorry, that keeps coming up. So that is when I am stationary. As far as moving to the left, I'm moving to the left when my velocity is negative. And I can use the graph in order to determine this. So my velocity is negative right here. So I can say that I am moving to the left from 0 to square root of 4/3. I include the point 0 because at the point 0, my velocity is negative, so I have a bracket around 0. I have a parentheses around the square root of 4/3, since at the exact point, square root of 4/3, I know that I'm stationary. And then I'm moving to the right when my velocity is positive. So that will be after square root of 4/3, all the way up until 5, since this is the interval that I care about. So then I'm moving to the right. From square root of 4/3 all the way up to 5. And this t equals square root of 4/3 is when I am stationary. All right, so that is part A. Part B, we want to graph the acceleration function. So the acceleration is the double derivative of the position function. So I know that acceleration is equal to f double prime of t, which is the derivative of what I just found to be the velocity. So it's the derivative of this guy, 3t squared minus 4. And this derivative is 6t. And that is just a plain old linear function. All right, our final objective here is to describe the motion of the dog. So as we saw in part A, from time equals 0 to time equals 4 square root of 4/3, the dog is moving to the left. At 4/3, the dog is stationary because it's turning around basically to move to the right. So from 0 to square root of 4/3 seconds, dog is moving left. At square root of 4/3 seconds, the dog stops and turns around. Maybe they saw a treat. And moves right. Until t equals 5 seconds. So that is how the dog is moving. So this is just it's a pretty simple example to show how velocity, position, and acceleration are all related to each other. Next, we are going to talk about growth rate. So if I have a function p equals f of t on the interval, say from a to b, then I have the growth rate is equal to the limit as delta t goes to 0 of delta p over delta t, which is equal to the derivative of p with respect to time. So if I have a function p, to find the average growth rate, I simply take the derivative of the function. We've been seeing this all term since day one. The average growth rate of a function is just the slope between the 2 points on the function, which is also the derivative. The instantaneous growth rate with respect to time is, we just plug in t into this guy right here. So it's dp of dt at t equals time we're interested in. So this guy should be a function. If I care about the instantaneous growth rate, I simply plug in a particular time into that function. So let's look at an example. The number of worldwide internet users in there's a typo here, in millions. In time t, where t is years after 2000, can be modeled by the equation p of t equals 6t squared plus 98t plus 431.2. So we want to use this function to approximate the growth rate from 2005 to 2010. So according to our definition up here, I see that my growth rate is change in y over change in x, basically. You can say delta p over delta t. Okay, well, my delta p is my change in y. So this is p of 2010, which is the year 10 since I'm after the year 2000, minus p of 5. And then my change in x, or time, is 10 minus 5. So if I were to plug in t equals 10, I would get p of 10 equals 6 times 10 squared plus 98 times 10 plus 431.2. This is 2011.2. So my first number here is 2011.2. P of 5 is equal to 6 times 5 squared plus 98 times 5 plus 431.2, which is equal to 1071.2. Over 10 minus 5, which is 5. And if I do the math here, this is 188. My units here is million, since I'm working in millions. And my y value was telling us users. My x value was telling us year, so this is 188 million users per year. So this is, on average, how our function p of t changed between 2005 and 2010. All right, what was the instantaneous growth rate of internet users in 2012? So the instantaneous growth rate, I simply take the derivative of my function p and I plug in 12. So in part b, dp dt is equal to, I take the derivative of my function here, and I get 12t plus 98. So then the instantaneous growth rate, in 2012, I just plug in 12 for t here. So dp dt of 12 equals 12 times 12 plus 98, which is 242. And again, we're talking about millions of users. So this means that in 2012, the rate of change in the number of internet users was 242 million of users. Of course, we don't know exactly when in 2012 this was the case, but at some point in 2012 it was. All right, and then we want to use this model to predict the number of internet users in 2021. So P of t is the number of internet users. So I'm simply going to plug in 21 into my P of t function, since that function is what tells us how many internet users I will have. So P of 21 equals 6 times 21 squared plus 98 times 21 plus 431.2. This is equal to 5,135.2 million users. So that's like 5,135,000,000, which is a lot of internet users. So that's just next year. We'll see if that's the case. So yeah, we can think about growth rate in terms of derivatives instantaneously, and then we can also think about growth rate in terms of change in y over change in x, kind of like we did in part A. Okay, we have one more application that we are going to look at today. That is average and marginal cost. So say I have a cost function c, and it gives the cost to produce the first x items in a manufacturing process. The average cost to produce x items is, we call this c bar. So c bar of x is equal to the cost divided by the number of items. That makes sense. The marginal cost, c prime, is the approximate cost to produce one additional item after producing x items. So this expression here, c of x over x, that is the average cost to produce a certain number of items, and then the marginal cost is the cost to produce one item after those that x number. So say we're producing 500 of something, we only know the average cost up to 500, and then the 501st item would be included in the marginal cost. So we have an example here. Suppose the cost of producing x number of double chocolate chip cookies is given by the equation c of x equals negative 0.03x squared plus 40x plus 75 for the first 1,000 cookies. We want to first determine the average and marginal cost functions. So the average cost function is this c bar of x, which is c of x divided by x. So my cost function here is negative 0.03x squared plus 40x plus 75, and then I divide this by x. So if I were to simplify this a little bit and cancel out an x, well, I can cancel out an x from the first two terms. So this becomes negative 0.03x plus 40 plus 75 divided by x, if I divide each term by x. My marginal cost is c prime of x. So this is my average cost. And then my marginal cost is given by c prime of x. So I simply take the derivative of my cost function. That will be negative 0.06x plus 40. All right. Now in part B, we want to determine the average and marginal cost for the first 50 cookies. So I simply plug in 50 into my two equations that I just found. So the average cost, C bar of 50, equals, I plug in 50 here, negative 0.03 times 50 plus 40 plus 75 over 50. This is approximately 40 cents. The marginal cost for the first 50 cookies so this would be the cost after making the first 50, would be C prime of 50 equals negative 0.06 times 50 plus 40, which is equal to 37 cents. So what this means is after the first 50 cookies made, the 51st cookie would cost 37 cents. All right, and then in part C, we want to determine the average and marginal cost for the first 950 cookies. Remember, our equation is valid for the first 1,000 cookies. So C bar, the average cost to produce 950 cookies, is negative 0.03 times 950 plus 40 plus 75 over 950. This is equal to 11.5 cents. That means the average cost for the first 950 cookies is 11.5 cents per cookie. And then our marginal cost, C prime of 950, equals negative 0.06 times 950 plus 40, which is equal to negative 17 cents. So if my cost to produce something is negative, that means that after the 950th cookie, I am making a profit. So in this manufacturing process, you have to make 951 cookies to make a profit, but that's how they do business, I guess. All right, that is our last example for the day. I hope you enjoyed these applications of derivatives, and I will see you all hopefully in the Zoom meetings. If not, I'll see you on Wednesday. Have a wonderful day.